In this tutorial video, we'll be looking at how to set up spawning, despawning, and even chain spawning using PoolKit. Firstly, we'll be using this scene here to make these cannons start firing lasers. From there, we'll get those lasers to explode and create debris with chain spawning. So let's get started. Firstly, let's take a look at the local pool. It's using a fixed array with pool protection turned off. We also have 3 prefabs that will power everything in this scene. We have the laser prefab, an explosion prefab, and some debris called the mini ruin rock prefab. The debris and explosion prefabs are also using instance recycling to keep their numbers under control. So let's get to building the spawner that will shoot the lasers. We can easily create a PoolKit spawner by right-clicking in the hierarchy and selecting PoolKit, Create Spawner. The spawner is a little far away, so let's move it closer to the cannons. This should make things easier to work with in the scene. Now that the spawner is pretty much where we want it, let's work through the spawner's tabs to understand how things work. Firstly, let's give the spawner a name. This makes it clearer in the scene view, as well as allowing us to easily grab it via the API. We'll call this the cannon spawner. Next, we can choose when it will start to spawn. By default, this is set to begin automatically on start. You can choose to use on-enable options instead, which allows you to make spawners into their own poolable prefabs. There are also options to only activate the spawner through scripting, or to block it completely by setting it to never. We'll use the automatically on start setting. We can now choose the duration of the spawner. We can spawn a single instance and stop, repeatedly spawn a specific number of instances, keep spawning for the duration of a countdown, or to simply keep spawning instances forever. For this example, we'll choose loop forever. The next option allows us to set up the frequency of the spawner. We can choose whether to spawn new instances using a fixed time interval, currently every 1 second, or to use a random range. We'll change this to use a random range and set the spawner to create new instances between every third of a second to every 1 second. This should make things feel more realistic and less robotic or predictable. Finally, we can choose how many instances will be spawned after every interval. Let's leave this at 1 instance for now, but you can spawn any number of instances every spawn cycle. The prefabs tab is where we can tell the spawner which prefabs we want to spawn. It can automatically detect if the prefabs we add belong to a pool and can be spawned, or whether they need to be instantiated. In this case, we only want to spawn a single prefab, the cannon lasers, so we'll drag and drop that into the new prefab slot now. Another cool option in this tab is the prefab selection mode. This drop-down list gives us a range of options on how the spawner should select from the prefabs below every time a new instance is spawned. It doesn't make any difference if we only have a single prefab, but works great if you are spawning from a variety of prefabs. The following options can be selected. Sequence ascending chooses the next prefab in order of the list, top to bottom. Sequence descending chooses the next prefab in reverse order of the list, bottom to top. Ping pong ascending selects the next prefab in order of the list, but when it gets to the end, it reverses and starts to make its way back to the beginning. Ping pong descending is like the previous selection, but in reverse order. Random will select a prefab totally at random. And random with weights allows you to give each prefab a random chance to be selected. When this is chosen, the list will also include a slider that represents the chance that prefab will be spawned. A 0% chance means it will never be chosen, and 100% gives it an equal random chance. We'll choose sequence ascending for now, although it's worth mentioning that selection modes are ignored if you only have 1 prefab. Let's move on to the Instances tab. This section allows us to set up how instances will be scaled, rotated, and parented. The first option in this tab is the parent mode options. We can ignore parenting, or reparent the instance to the spawner, the spawn point if we're using a transform list, which we'll look at shortly, or to a custom transform that you can set. We'll leave this set to ignore for now. The next option is the instance rotation mode. We can choose to rotate the instance using the default settings of the prefab, the rotation of the transform of the spawner, the rotation of the current spawn point, if there is one, a custom rotation, or a totally random rotation. We can also apply an offset to the rotation in many cases. Finally, we have the instant scale mode. These settings are very similar to the scaling options found on the pool, but allows you to use the scale of the spawner itself as an additional option. Now let's move on to the spawn points tab. This section is all about where the instances should be positioned in the scene. There's lots of options to control this. By default, the spawner is set to always spawn new instances at the spawner's own transform position. We could choose to use a list of transform objects, which we'll come back to in a moment. Let's take a look at setting up a local position list. This uses a list of vector3 values to position the spawn points in the scene. The next option asks us what these positions are local to. By default, the values will be local to the spawner, but it can be any object you like. To give an example of how this works, let's set up the custom local transform to be the pools object. If we drag and drop that into the spawn local to field, you can see that a big line has just appeared in the scene view. This shows us how the vector3 values will now be positioned relative to the pool instead of the spawner. As I modify and add new positions to the position list, you can see the changes updated in real time. If I switch back to using the spawner instead of the pool, you can see that positions have changed to be relative to the spawner's transform position. If I want to make further changes to the spawn points, the labels in the scene view make it easy to know which values I should modify at a glance. This makes everything extremely easy and intuitive. Just like the selection modes found in the prefabs tab, we can also choose how spawn points will be chosen by the spawner in the same way. This also includes the random with weights mode, which adds the random chance slider to the spawn point list. Now that we've covered local positions, let's take a look at the global position list. This is very similar to the local position list, with the exception that this uses world coordinates instead of local ones. You can now see that these positions are local to the scene's origin rather than any other objects in the scene. However, setting up the cannons requires a different approach. Let's go back to using the transform list. We're going to use 5 transforms to determine the spawn point of our lasers, one for each cannon. If we inspect the cannons, we'll find that they all have been set up with a child game object called gun spawn point. This is what we'll use to configure our spawn points. To do this, we simply drag and drop each one of the gun spawn points into the slots we just created in the spawner. The spawn points are all set up and good to go. You'll notice that this setup allows us to move the spawner without breaking the spawn point positions. Last but not least on the spawner, we have the events tab. This section allows us to optionally set up delegates and Unity events to get callbacks for when the spawner's state changes. Enabling delegates generates a code snippet we can use to work with the API. You'll notice that even the correct name of the spawner is included too. We can get callbacks for when the spawner starts, stops, pauses, resumes and ends. We can even get a callback to receive the transform of each object that is spawned. Now that we've finished setting up the spawner, let's take a look at the results. The lasers are already set up to use PoolKit's powerful Despawner component. As you can see, they're working great. They're colliding with the pillars to chain spawn the explosion and debris prefabs. If we take a look at the profiler, we'll also find that we're doing great with garbage collection by having 0 memory allocations. To understand how this is all working, we'll need to take a look at the Despawner component. Let's do that now. First, let's create an empty game object and use that to explore the Despawner. Even though we'll delete it later, we'll call it test Despawner for now. Let's go ahead and attach a Despawner component and take a look at how things work. The component's first tab is the Despawner tab. This is where we set up how this game object should despawn. A number of powerful events are included. Firstly, we can use a simple countdown. In this case, the game object will despawn after 5 seconds. We can also use a countdown with a random range. The current settings will despawn the game object randomly between 4 and 6 seconds. The next option is to wait after a particle system finishes. Because we don't have a particle system on this object, the editor is reminding us to add one. It's worth noting that most of the events will allow you to choose where the source component is located. In this instance, the source is the particle system. It's currently set to be found on this game object, but you can also tell the despawner to look for it on another child object, or using a custom manual setup which is discussed more in the documentation. Moving on, we have the after audio source finishes option, which will despawn this object after an audio source finishes playing its audio clip. Then we have the After Physics Overlap Event option. This is a beast of an event and is incredibly optimized to allow you to use physics-based collisions without allocating any memory. You should try to set up all of your physics events using this mode if possible. This event doesn't even need a collider. It works by calculating a physics shape over the current game object to check if it overlaps with any others. If a valid collision is detected, the object will despawn. First, let's move the test despawner object so we can see it in the scene view. Now, we'll be able to see the physics shape that will be overlapped and tested for collisions. You can also choose what kind of physics shape to use. The options are a 3D sphere, 2D circle, 3D box, and 2D box. We'll go back to the default 3D sphere. Next, if we're using a 3D shape, we can tell the despawner whether we should include triggers in the collision checks. We can choose either to use global physics settings, ignore triggers, or collide with triggers. All settings allow you to use a local position offset, which you can use to recenter your physics shape. Finally, we have a radius or scale field that we can use to resize it. We have some additional settings under the options section. If we have a rigid body on this game object, we can choose to automatically reset its velocity every time this is spawned. In addition to the physics event, we can also set a despawn countdown. Under current settings, if a physics collision doesn't despawn the object for 5 seconds, it will be despawned by the countdown. Finally, we can also choose to filter collisions using a layer mask and game object tags. Only collisions found to be using a layer found in this layer mask can cause this to despawn. We can also further limit game objects by specifically including what tags are allowed. We can add as many tags as required by pressing the green plus arrow. If no tags are in the list, they will be ignored. The next group of physics events starts with the After Physics Collision event. These routines use the common Unity physics methods, which unfortunately do create some garbage collection in memory. This is a Unity physics limitation rather than a PoolKit one. The good news is PoolKit is so optimized that you shouldn't generate any more garbage collection than if you had used it yourself in a custom script. To set up these types of physics events, a collider is required. You can choose whether to look for a collider on the current game object, on a child object, or using a custom manual setup. We then choose which Unity collision methods to use. You simply tick the checkbox next to the ones you want to use, and PoolKit uses unique optimizations that only include the code required for each one. Just like the previous physics event, you can also reset rigid body velocities and set up a despawn countdown. Filtering collisions by layer and tag is also possible. The remaining physics events follow the same pattern. The After Physics Trigger event works in the same way, but allows you to use Unity's trigger physics methods. The same applies for After Physics Collision 2D and After Physics Trigger 2D. The last option is to only despawn this game object if it is called by a script. You can see that the despawner creates a handy code snippet to show you how. Next, let's take a look at chain spawning. Chain spawning is a PoolKit feature that allows you to immediately spawn new objects when the despawner is about to despawn. This effectively becomes a specialized spawner in its own right. We can spawn as many prefabs as we want by pressing the green plus arrow in the bottom right. To set up how it will be spawned, we need to drag in a prefab into the slot. For this example, we'll use the cannon explosion prefab. Firstly, we can apply a spawn option to the prefab. We can choose to always spawn this prefab or only if it was a physics event, or specifically not a physics event. We can also choose never for debugging purposes. This allows us to set up situations where, for example, an explosion can be spawned if this instance collided with another game object, or just spawn into a small puff of smoke if it was triggered by the timeout. This enables us to build some really cool configurations. Next, we choose where the instance should be positioned. Our initial position can be this transform, another child transform, or the position of the last collision if we were using a physics event. We can then apply a local position offset with the result, and even add a further randomized offset using a random range. After the position is set, we can configure its rotation. We can use the default rotation of the prefab, the current rotation of this transform, a custom rotation, or a random one. We can also apply an offset to the rotation using the field below. We can then proceed to scale the instance using familiar options from other components. However, When one of the custom options is selected, a new drop-down will appear allowing you to process the scale result in a variety of interesting ways. This includes multiplying it with the local scale, or with the smallest, largest, or average vector, among others. This gives you a huge amount of control over how these instances will be scaled. Finally, you can repeat how many times this prefab will be spawned using the settings above. This works especially well with the apply randomize offset setting, which randomizes the position so that they won't all be in the same place. You can add as many chain spawn configurations as you want in the list. You can also delete and reorder them with easy to use shortcut buttons. The last tab is the Events tab. This works in a very similar way as the Events tab in the Spawner component. Enabling delegates will create a code snippet we can reference, and we can set up Unity event equivalents too. We can receive a callback when this object is despawned, as well as receive the transform of instances that are chain spawned. Another really cool feature is the ability to receive the game object that collided with a physics event. This can help you build an enormous amount of functionality, including a damage system right from the despawner. Now that we understand how the despawner works, let's delete this game object from the scene. Also, let's remind ourselves on how the scene was playing out. As you remember, the lasers would shoot into the pillars and chain spawn explosions and debris. Let's take a closer look at the despawners used to achieve all this zero allocation coolness. The first thing to note is that all of the pillars in this scene are using the rocks game object tag. Let's look at the simplest prefabs first, starting with the explosion prefab. If we place it in the scene, we can select its particle systems to remind us what prefab this is. The despawner on this particle system is using a simple countdown of 4 seconds in order to despawn itself. Let's remove that from the scene and take a look at the debris prefab, which I've named the mini ruin rocks. These are essentially small cubes, and they are also set to despawn themselves after a countdown of 3 seconds. It's worth noting that both the explosion and the debris prefab here do not use any chain spawning. But that's where the lasers come in. Let's take a look at how this is all set up. First, let's click on its particle system in the hierarchy in order to see what the laser will look like at runtime. The next thing to note is the PoolKit bullet script that is attached to the prefab. This is a generic script used in other examples, but the only part of the code relevant is the fixed update method. We tell the object to move along its forward direction using a certain speed every frame. If we return to the despawner, we can take a look through the settings. The laser is using the after physics overlap event. This is the most optimized physics event in PoolKit. The physics shape is set to use a 3D sphere. We're using global settings for triggers and not adding any positional offset. The radius of the sphere is set to 0.5. Rigid body velocities are reset every time this is spawned, and we've also set up a despawn countdown of 2 seconds if the laser doesn't collide with any other objects. The layer mask is set to everything, which in effect allows collisions on any layer, but we have added a specific filter tag called rocks. This is so the lasers can collide only with the pillars in the scene. If we switch to the chain spawning tab, you can see that when the laser despawns, it will chain spawn the explosion and debris prefabs. Let's take a look at the explosion prefab first. You'll notice that we've set a spawn option to only allow the explosion to be created on a physics event. In this case, this means it will only be spawned if the laser collides with the pillar, but not with a timeout. The explosion's position will be set to match the laser's position. No local offsets or randomizations will be applied. The rotation of the explosion will be totally random, and will then be scaled using a proportional range. This keeps the scale uniform, and will use the range of 0.8 to 1.5. There will only be one instance of the explosion spawned. Moving on, the debris prefab named Mini Ruin Rock will also only spawn on a physics event. Just like the previous prefab, it will also be spawned at the position of the laser's transform. However, a randomized range will then be applied to the position. The debris will then be rotated using its own default prefab settings. It's then scaled using a proportional random range to keep the objects a uniform size. The scale range will be between 0.2 and 0.4 units. Finally, 8 instances of the debris prefab will be spawned using the same settings. Because of the randomization offset in their positions, they will appear to spawn in slightly different places, which is a great way of spawning multiple instances in a single configuration. And there you have it. When all of this comes together, PoolKit allows you to create amazingly complex scenes while simultaneously optimizing your games to use as close to zero memory allocations as possible. I hope this video has sparked some great ideas in how you can use PoolKit in your own games. Thanks for watching.